Hey everyone, welcome back to Chem Story. Today, we're diving into molecular orbital theory, or MO theory. It's a powerful way to understand how covalent bonds form by looking at how atomic orbitals combine and form molecular orbitals that electrons can occupy. Let's break it down step by step. Alright, let's talk about molecular orbital theory. There are a few different ways to explain how covalent bonds form, and MO theory is one of the big ones. According to this theory, when atoms bond, their atomic orbitals don't just merge, they actually interact to form brand new orbitals called molecular orbitals. Think of it like this. When two atoms come together, their electron clouds don't just blend together randomly. Instead, they overlap in a very specific way that creates a new distribution of electrons. And here's the key idea. This process takes the phase of the atomic orbitals into account. If the orbitals are in phase, they reinforce each other and form a bonding molecular orbital, which is more stable. But if they're out of phase, they cancel each other out, and that gives you an antibonding molecular orbital instead. So MO theory tells us that bonding isn't just about atoms sticking together. It's really about how their electron clouds interact and reshape the entire electron distribution. And this idea becomes super useful when we want to explain things like bond strength, molecular stability, or even magnetic properties. Now, let's take a closer look at how this combination actually works. It all comes down to wave interference, which means that the way atomic orbitals interact depends on whether their waves align or not. But first, what exactly do we mean by wave here? Well, in quantum mechanics, a wave represents the probability distribution of where an electron is likely to be found. Instead of picturing electrons as tiny particles locked in place, it's more accurate to think of them as spread out over a region, like a cloud of probability. This distribution is described by something called a wave function, which plays a crucial role in determining the shape and energy of atomic orbitals. Now, here's where interference comes in. If two atomic orbitals combine in phase, meaning their wave functions match up and reinforce each other, they create constructive interference. And what does that lead to? A bonding molecular orbital, which has lower energy and helps stabilize the molecule. When electrons occupy this bonding orbital, they hold the atoms together more effectively, making the molecule more stable overall. But what happens if the atomic orbitals combine out of phase, meaning their wave functions are opposite, and cancel each other out? In that case, we get destructive interference. Instead of forming a stable orbital, this creates an antibonding molecular orbital, which actually raises the energy and makes the bond less stable. There's an important principle to keep in mind. The number of molecular orbitals formed is always equal to the number of atomic orbitals that combine. So if two atomic orbitals combine, they always form two molecular orbitals, one bonding and one antibonding. This rule ensures that we account for all the atomic orbitals in the system. Now, let's break this down. A bonding molecular orbital has lower energy than the original atomic orbitals. Since electrons naturally prefer lower energy states, this makes the bond more stable and helps hold the atoms together. On the other hand, an antibonding molecular orbital has higher energy than the original atomic orbitals. And because of this increased energy, putting electrons in an antibonding orbital can actually weaken the bond or even prevent it from forming altogether. By understanding these concepts, we can better predict and explain the stability and bonding properties of different molecules. Now let's take a look at the molecular orbital diagram of the hydrogen molecule. When two hydrogen atoms come close together, their 1s orbitals overlap, forming new molecular orbitals. In this process, two new molecular orbitals are formed. The first one is the sigma bonding molecular orbital. It has lower energy than the original atomic orbitals, and that helps stabilize the molecule. The second one is the sigma star antibonding molecular orbital. This orbital sits at a higher energy level, and if electrons go into it, it can actually weaken the bond, or even prevent the molecule from forming at all. So, how are the electrons distributed in a hydrogen molecule? Well, each hydrogen atom contributes one electron, giving us a total of 2 electrons. These 2 electrons go into the lower energy bonding orbital, and that's what stabilizes the molecule. If you look at the molecular orbital diagram of H2, you can clearly see why the molecule forms and why it's stable. And the cool thing is, this same idea applies when you're analyzing other molecules too. Now, let's apply this concept to the oxygen molecule. Each oxygen atom has both two s and two p orbitals. And when they bond, these atomic orbitals don't stay separate. They combine to form a new set of molecular orbitals. So, just like with hydrogen, we're building a whole new electron distribution, but this time with more orbitals and more electrons involved. First, the two s orbitals combine, and just like before, they form two molecular orbitals. One is a sigma 2s bonding orbital, and the other is a sigma star 2s antibonding orbital. The bonding orbital has lower energy, while the antibonding orbital sits higher up, just like we'd expect from constructive and destructive interference. Next, the two p orbitals interact, and this gives us both sigma and pi molecular orbitals. The sigma 2p orbital forms from the head-on overlap of two pz orbitals, and that creates a strong bonding interaction along the internuclear axis. On the other hand, the pi 2p orbitals come from the sideways overlap of the 2px and 2py orbitals. These add extra bonding interactions, but they're a bit weaker than sigma bonds. Now, just like before, we also get antibonding versions, sigma star 2p and pi star 2p orbitals. These sit at higher energy levels, and if electrons occupy them, they can reduce the overall stability of the molecule. The oxygen molecule has 16 electrons, and these electrons fill the molecular orbitals in order of increasing energy. The last two electrons end up in the antibonding pi star 2p orbitals, and here's why that matters. Because those orbitals are only half filled, oxygen ends up with two unpaired electrons. That's what makes O2 paramagnetic. It gets attracted to a magnetic field due to those unpaired electrons. So by looking at the molecular orbital diagram, we can understand not just how oxygen bonds, but also why it behaves the way it does magnetically. And the same idea applies to other molecules too. MO theory gives us a powerful way to predict molecular stability, reactivity, and even magnetic behavior. Alright, let's talk about why energy goes down when a covalent bond forms. When two atoms come together and form a bond, the whole system becomes more stable, and that stability comes from a drop in energy. But what actually causes that energy decrease? There are two main reasons. First, bonding molecular orbitals are formed. When atomic orbitals combine, they create new molecular orbitals, and in the bonding case, this lets electrons spread out more. In other words, electron delocalization increases, and the more spread out the electrons are, the lower the overall energy, which makes the bond more stable. Second, the electrons in the bond are now attracted to both atomic nuclei. They're no longer pulled toward just one atom. Instead, they're drawn into the space between both nuclei. That region is more stable, and as electrons settle into it, the total energy of the system decreases. So to sum it up, energy drops during covalent bond formation because electrons are more delocalized, and they're stabilized by the attraction from both nuclei. And that's what makes covalent bonds so effective. They pull atoms together into a lower energy, more stable arrangement. Alright, that wraps up our deep dive into molecular orbital theory. We looked at how atomic orbitals combine to form molecular orbitals, how constructive and destructive interference leads to bonding and antibonding orbitals, and how this theory helps explain molecular stability and magnetic behavior. By using molecular orbital diagrams, like those for hydrogen and oxygen, we saw exactly how electrons are distributed and how that affects a molecule's properties. This perspective goes beyond just visualizing bonds. It gives us a deeper understanding of how electrons actually behave inside molecules. Thanks for joining me today, and I'll see you next time on Chem Story.